Hi everyone, I am Sue. I'm a second year physics student. In the first lecture of this Schrödinger's lecture, let me breathe, okay. We will be making an analogy between geometrical optics. By the way, can you hear my voice? Okay. Analogy between geometrical optics and classical mechanics to derive the fundamental idea of the wave mechanics. And then we will see that ordinary mechanics is only an approximation which, okay, why is like, I don't know, let me read a little bit, okay. Ordinary mechanics is only an approximation of wave mechanics. Finally, we will obtain time-independent Schrödinger equation by considering an electron in the hydrogen atom. Okay, if you have any questions during the talk, especially Ekin, please feel free to ask. I will try to do my best to answer.
Can you open the lights of the wall?
Actually, it doesn't open. There's...
O üçünden biri açıyor olması.
I think it's okay. Maybe you'll understand better when I start. Okay, now we will start our analogy by considering a mass point. Is it like too thin? Okay, if you can see it, right? We will consider a mass point moving from point A to point B, and its motion is described by the principle of least action. This is delta from A, B to T, dt. Here T is the kinetic energy, and you see that it depends on delta T. Now we will play with this a little bit and obtain this and get rid of this time dependence. So here, this is a conservative field and energy is conserved. So total energy is, let me write it here, total energy is potential energy plus kinetic energy. And kinetic energy is, as we know, mv squared. Here, v is the velocity of the mass point. So we would like to obtain 2t. We can write velocity in that form. Yeah. Let me find something from in here. 2t is, let me look at here, yeah. dt squared. Multiply both sides by m, 2mt and m dt squared, and take square root of it. So I'm doing it to put it here. You write ds over dt t. Fine. Are we good? Okay. So we can write kinetic energy in terms of total energy and potential energy. We will write ds over dt to e minus v. So we can plug this in this equation and obtain the new form of it. Minus v, and now it's not t ds. Okay. Now we will move on. With light signal. time, we consider a light signal from point A to B. Let me write it. Okay, and its motion is described by Fermat's principle of least time, this time. So this is ds, the path, and u, the velocity, is equal to 0. So now if we postulate that u, the velocity of light, is equal to c over 2m minus v. Here c is something depending on coordinates, but not on, sorry, no, forget about it. It depends on energy, it may depend on energy, but it cannot depend on coordinates. This is not velocity of light, please don't confuse with it. This is c, and we will find what we need for c in a second. So if we plug this u in this equation, we will obtain 2m minus v, yeah, or c. So notice that this and this same. So this is the first step of our analogy. We could coincide at least the geometrical explanations of the mass point and light signal. Are we good up to this point? Okay. This energy dependence will help us to push our analogy a step further, because we will introduce a wave mechanical property, which is frequency, by introducing energy in hf, where f is the frequency and h is the Planck's constant. Okay, yeah, we will use this. Now our question is, can we make this light signal, can we make a point like light signal exactly the same as our mass point? At first sight, okay, before saying that, let me write the velocity of the mass point more explicitly. Okay, 2m. I'm writing the kinetic energy in terms of total energy and potential energy, and over m. Yes. So we obtain the velocity of mass point like that, and the velocity of light signal like that. So they seem, what was the word for it? Inversely, they seem inversely proportional. But actually, we want to. This is the phase velocity. Phase velocity of light, but I said that can we make a point, how to say, point like light signal. So I'd like to consider something called group velocity. Group velocity, G, okay. So group velocity will represent a point like light signal's velocity, envelope's velocity. So I'll do it. It's defined as dV over dt. This is angular frequency, wave number. I will write it like F D 2 pi over lambda, and the F the what was it? Yeah. So I will use group velocity, and I will write 1 over group velocity from here. E F over U, and from this, so I'm introducing this, I'm using this by writing it like in terms of energy. Are we good? You have a question? No? Okay. So.
What is the origin of mass term?
Huh? Sorry?
Why there is a mass in some equation corresponding to light? Why there is a mass?
We proposed this.
Okay.
I proposed it. Not I, Schrödinger. Okay. So, but we want to make a correspondence between them. So, I want to assume that group velocity of the point like light signal equal to mass points velocity. And let's see what happens. So. Okay, I will write 1 over g by plugging this u in this here. Okay. 1 over d. Okay, oops. 2m a minus v over c. Okay. And this is 1 over g. Since we assume that group velocity equal to v, I will write 1 over v, which we found here. So, yeah, this is 1 over v. Okay. And we notice that this is equal to this 2m a minus v, and we want to use these two equations. They are equal, so we write them like energy over C minus 1 So I think you noticed this is a constant. So since potential energy depends on coordinates, and we said that C is only depending on energy, only way to secure this is making this part 0. So is equal to 0, and we see that C is equal to E with our assumption. So from now on, we will use the velocity u in this form. Okay. in our first analogy, we made a correspondence in terms of their geometry. Now we are making a correspondence in terms of their dynamical laws by introducing the velocity. Yes. Do you have any questions so far? Because we have completed lots of important things in terms of their correspondence. Anything? Is everything clear? Clear? Okay. Now I understand from Ruja why he's making it too hard. Okay. Okay. Now we are describing the motion of a mass point in terms of frequencies and such velocities. So we are trying to introduce a wave mechanical properties because we want to obtain a theory that works for very small systems, which ordinary mechanics cannot. So maybe we will now find the approximate order of magnitude when we expect ordinary mechanics to fail in a special case. Okay, let me write wavelength, velocity over frequency, and I will use the energy equation. Okay, I will write it again because I can't find it now. Okay, so I plug this here and frequency A E over H. I obtain this 2m E minus V, and this is V showed here, M V. Also, not also, for simplicity, we will assume a circular path having a radius A. And by using ordinary mechanics, we will write angular momentum, VA, over 2 pi. So, by using this, these last two equations, by using them, we can obtain lambda over radius, 2 pi over n. So so we want the path is big enough and comparable to the wavelength, because as the wavelength gets higher, the wave property gets significant for our case. So in the hydrogen atom, for our case, we consider hydrogen atom, and its size is approximately in the order of 10 to the minus 8 centimeters. So we want this to be comparable to this. So lambda should be also at most in the order of 10 to the minus 8. I think, yeah, I will delete this part. Let us now consider a very mechanical treatment of a case. which is inaccessible in ordinary mechanics, let us consider an electron in the hydrogen atom. If we say that the particle has a wave motion, it should have a wave equation. So at the end of our considerations and calculations, we will obtain a wave equation for that particle. Now we will approach the problem in a similar way that we do as in an elastic body. So let me consider fluid which has a pressure P, and for the fluid we can obviously write an wave equation, which is the square this, the standard way of solving a partial differential equation like this is to try this. And the time dependence here. Let's plug this in here. So, okay. See? Okay. Square. 0. So we obtain this. Now, if we solve this, the solution for psi and the solution that's satisfying the boundary conditions, we see that this frequency cannot take all the values, but take some discrete set of frequencies, which are called characteristics or proper frequencies. We obtain this, and let us turn back to our electron. I'll delete this part. So for our electron, we also expect it to have some quantity that also satisfies this wave equation. Okay. So yeah. So we need to again using this. And we, for our quantity P, we make an assumption again and do 2 pi I H I. Yeah. And if we take the second derivative, time derivative, we obtain 4 pi square E square H square P. Okay. And we plug this and this in the wave equation. let's plug in. It's in. Right. Okay. By the way, we are replacing the letter P with psi because we will obtain the wave function. I mean, psi, this. So we replace just P with psi. And 8, no, this square of this over E square, and square 4 pi square E square. No, I wrote it upside down. Sorry. Okay. Again. And I will write with h bar, which is h over 2 pi, this equation. So we obtain the the time of independence Schrödinger equation. Maybe I can get an upload. It was a joke, but thanks. Okay. Yes, sure.
In the equation you put in the rectangle, like, it says minus 1 over u squared.
Yeah.
And there...
of course, because there is also a minus.
Other minus.
Yeah, thank you. So it's plus.
Yeah.
Thanks. And that was the most important thing we wanted to do. And then we can solve it for hydrogen atom, which I won't solve but write directly. A constant minus, what is it? 2 pi squared and v squared or n squared. And for a bound electron in the hydrogen atom. Yes. In the next lecture, Ilgun will present you the how Schrödinger equation explains some experimental findings, such as Riemann and Stark effects. And she will be investigating, she will be driving time-dependent Schrödinger equation. That was all from me. I hope you enjoyed. And I can take your questions now. Was it?
So we started with an assumption and we moved on from there. Does Schrödinger make any point about if the assumption is correct or not? Because if the initial assumption is not correct, then it might not make sense, maybe.
I think as it works, he moves on, as far as I understand.
We assume that this equation is axiomatic. Like, we don't know where it comes from the beginning. Still, it's an open question. Actually, Griffiths is the person that derived this equation from the first principles, and it has and it's a parenthesis. It says that if you can find something, please contact the Nobel office so that you can get a report. Still, there is still an open field. Actually, like quantum foundations is actually trying to move how we can for this Schrödinger equation. There are several candidates, but each has some drawback. But the most, like, how can I say, promising one is like they are trying to come from the probability theory to this point, and like there is some good things from that. Like you can take your classical probability theory and set some restrictions like no signaling, blah blah blah blah, and you can actually deduce from the ordinary probability theory from this one, like from Kosovo axioms to here. There's a nice way, but there's some still holes from that, like how you can explain the measurements, blah blah blah. I will explain those blah blahs to you if you want.
Yeah, any questions? Yes, sure.
What does this equation in the end really tell us?
Yeah, it tells us that a particle, not like a particle, has a wave equation. I'm so angry about it. No, it's so cute.
What is psi, for example?
This is the wave function.
Like Schrödinger equation is basically saying that kinetical energy plus potential energy equals to the total energy. That's it. If you think basically it's just it is just that.
It's just
But the point is that we still don't know where it comes from. Jacob.
So psi depends on x, y, and z, right?
X, Y, Z, and yeah, time also.
But
But in your case, it's not.
Not time, in
is
my
it some
case.
kind of vector? What does it mean?
You can think of it as a vector if you think it's an element of Hilbert space.
It's an exercise for you.
It's
It's an exercise.
you can put all real functions as a vector, right? Like just consider them as a lookup table, infinite size, so they are vectors. And actually, there is a formulation for that in quantum mechanics that you can think every wave functions as a vector, so that you can use the power of linear algebra.
Yeah.
Actually, it will be a good exercise. Like we can do it here. No,
Yeah,
not an exercise. But
feel free to comment on it.
I can save the Sue from this driving also. You can ask me questions.
Yeah, I mean, he's the master. Yeah.
Any questions? Ask anything.
You?
I have no questions.
Really?
I see it like
Am I that good?
It's my 7th year in Bilkent, so I saw it like for 7 years.
Okay. Do you have a question at all? Afiyet olsun. Bana mı soruyorsun? Sağ ol. Akşam yemeği.
Shouldn't it be h bar squared?
O H bar squared.
Öyle mi oluyor?
Evet. Hiç benzemiyor şöyle bir equation. Böyle söyleyeyim sana.
Şu an doğru.
Bence doğru değil.
Really? Okay, let me check it.
Ben şey olarak yazıyorum ben. H kısa eşittir E kısa yani.
Ha, o benim. Ya.
Hamilton'un cinsinden yazıyorum. İlk çıkarımlarını düşüyorum. Benim işte hepsi var.
I have last seen these in math moment. As a biologist.
Sorry.
As a biologist, this is my yeah. Yeah. Nothing.
Okay, any questions, Anila?
Like, we found this, we got both, we passed on to chemists got both, they passed to you.
Yeah.
At least we can apply. Neyse. Yeah,
Bir şey
if
demiyorum buna. Bir şey demiyorum buna.
demedim.
Hayır, cidden apply etmek keyifli etmediği konusunda felsefi tartışmalarım.
Okay, if there are no other questions, thank you all for coming.